Now imagine the solar wind is blowing against our magnetic field all the time. And so our magnetic field makes this bubble in space. Most of our, what we call heliosphere, our solar system, is taken up by the sun's magnetic field. But we've got our little bubble of magnetic field that we call our magnetosphere. Every planet with a magnetic field has a magnetosphere. But if you're the magnetosphere, and I'm the solar wind, and I'm pushing against you at 400 kilometers per second, you're going to have to resist that, right? And so what it does, the solar wind, it scrunches up the side of the magnetosphere that's facing the sun, and we refer to these things, so you have to kind of put yourself in this mind frame where you're not on the Earth anymore, but you're some alien out in space looking down on our solar system. And so we call that side the day side, because no matter what time of day it is here on Earth, the side facing the sun is the day side. And the side away from the sun is the night side. And the fact that the Earth is spinning around inside there, we don't really care about. So the magnetosphere is all compressed on the day side, and it's stretched out like a windsock on the night side. Now, I mentioned the sun has a magnetic field. The solar wind, as it's coming out, carries particles. It also carries magnetic field. And we have a magnetic field. So the sun's magnetic field, our magnetic field, interact with each other. And so in addition to just this pressure on the front of the magnetosphere, you've got sun's magnetic field, our magnetic field. They can be in the same direction where they don't interact very much. They can be opposite directions where it turns out then they can interact a lot. One of the big breakthroughs of space physics was understanding that magnetic fields can interconnect or they can reconnect. And Linda mentioned this mission, the Magnetospheric Multiscale mission that's operating right now. It's a NASA mission. That's what we are trying to understand, is this magnetic reconnection. It can't happen in a vacuum. Magnetic fields can't interconnect in a vacuum, but they can when there's discrete particles, like protons and electrons, like we have in the plasma. So when that happens, when the sun's magnetic field points south and our magnetic field points north, they interconnect and it turns our entire magnetosphere into an electrical generator. And the amount of electricity that's generated is enormous. One of the things that does is it energizes electrons that can hit the atmosphere. When that happens, it makes the atmosphere glow like a neon light bulb. And that's the northern lights, or the southern lights. Or aurora is kind of the generic term, aurora borealis and aurora australis. So the biggest manifestation, the obvious manifestation of space weather that we can see is the northern lights. Just throw it out. Has anybody here seen the northern lights? Has anybody seen the northern lights in New Mexico? No. All right, that's awesome. Yeah. Was that one of the best things you ever experienced? I have only seen them a few times, but you guys are welcome to jump in. Yeah.
How was that possible?
One of the best things that I've experienced in my life. All right, don't tell my wife.
Or your children. How does it reach that far south?
To New Mexico?
Sure.
Good. So the northern lights, you don't actually see the northern lights at the North Pole. And the reason for that, and this is now where we get into kind of the interesting magnetospheric physics part of all of this, which is where we fly satellites is in our magnetosphere. And so the space weather that we care about most, especially here at the lab, is not the stuff that happens outside of our magnetosphere, but it's the stuff that happens inside of our magnetosphere. So you get the solar wind, it's coupling energy into the magnetosphere. That energy gets transferred out to the night side, what we call the magnetotail, the windsock part. And it stores up energy, stores up energy, stores up energy, and it gets squished and squished and squished until it can't get squished anymore, because you've got, imagine this magnetic field line that's like this, and you squish it, pretty soon you're going to get those oppositely directed magnetic field lines. They reconnect. Now you release a whole bunch of magnetic energy. Some of that energy snaps back towards the Earth. Some of it goes down the tail towards Jupiter. The stuff that snaps back towards the Earth comes into a region closer to the Earth, actually very close to geosynchronous orbit, where we have a lot of our satellites. And so that's the magnetic field lines that maps to are not the ones that go straight up out the pole. They're the ones that go to a particular region in our magnetosphere. And so the aurora make a circle around the pole.
Saturn imagery, that's really great pictures.
Yes, the Saturn imagery, but the Saturn imagery, so the Jovian aurora, the aurora on Jupiter and the aurora on Saturn are actually created by different processes. They're more related to the moons.
We're gonna cut that off.
All right. But we also get this ring. It's called the auroral oval. And we're lucky, the Earth's magnetic field is not aligned with the rotational field. So it tips, and it tips down towards Michigan. So we actually get to see the northern lights at much lower geographic latitudes than anybody else on Earth. So you don't have to go up to northern Siberia, you don't have to go up to 80 degrees latitude. You can go up to 66 degrees latitude or so. But when you get a lot of energy coupled in, I am getting to your question. When you get a lot of energy coupled in, then the open field lines, the field lines that are not connected back to the southern hemisphere, that region becomes bigger. And so to become bigger, it means it moves down to lower and lower latitudes. So the bigger a storm, the lower the latitudes the aurora have. Often when we get aurora at low latitudes like this, it just looks like a red glow in the sky. The first aurora I saw was in Boulder, and I thought there was a fire reflecting off the clouds. And one of the things, if you ever want to know, am I seeing the aurora? The thing to look for, don't look for clouds, look for stars. Because if you can see the stars, it's not light reflecting off the clouds. And so you see these great pictures of the aurora where you get these huge curtains and stuff, and you can see the constellations through the aurora, because the aurora is just the atmosphere itself glowing. It's not reflecting off of it. That was a great question. What else did I want to talk about?
What's the next mission that you're writing your proposal for?
Oh, yeah, so that's a cool question. So the rocket experiment that I'm writing a proposal for is a little esoteric. So let me tell you about the satellite mission that we're working on that we hope there will be an opportunity to propose next spring. So the one that I'm most involved in, it's the Van Allen radiation belt probes. I was talking to some people at the lab recently about when did I get started on that, and it was 1998. So these satellite missions take a long time. The one that we're working on next